we've been working with matrices. So in this section we're going to learn how to solve systems of equations using an inverse matrix. Before we talk about an inverse matrix though, we need to talk about the identity matrix. And we did talk about it a little bit last time. The identity looks like this. That's an identity for a 2 by 2. A 3 by 3 identity will have 1, 0, 0, 0, 1, 0, 0, 0, 1. And the diagonal is always 1s and every other entry is 0. So for every square matrix, and your notes don't look like this, if you have a square matrix and you multiply matrix A times the identity, or the identity times matrix A, you'll get the same thing you started with. Here's an example. Do y'all have an example on your page? 3, 4, -2, 5. Do you have this? Okay, write it down. If you multiply this times 1, 0, 0, 1, you got a 2 by 2 times a 2 by 2. Can you do it? You can do that multiplication. And furthermore, the answer that you get is a 2 by 2. So this entry right here comes from multiplying row 1, column 1. So you'll do 3 times 1 plus 4 times 0. We get 3. This entry, you'll do row 1, column 2, 3 times 0, and 4 times 1. So 0 plus 4, we just get 4. This entry right here is row 2, column 1, -2 times 1, plus 5 times 0. We just get -2. And the last entry, -2 times 0, plus 5 times 1, we get 0 plus 5, or 5. So always, if you multiply a matrix times the identity, you get back the same matrix you started with. And this is the one time when it doesn't matter. Even if I switch it and do it in the opposite order, I will still multiply and get the identity. So we're going to work with that here in a minute. Multiplicative inverses for real numbers. Real numbers, let's change this and make this say an S. Multiplicative inverses of real numbers. Two numbers whose product is 1. Two numbers whose product is 1. So here are some examples. 1/3 and 3/1. If you multiply those fractions straight across the top, straight across the bottom, you'll get 3/3 or 1. 1, as it turns out, is the identity for real numbers. So 1 is to real numbers as the identity matrix is for matrices. And so anytime you multiply multiplicative inverses, you will always get the identity. That's true for matrices too. The inverse matrix is a matrix that, when multiplied by the original, will equal the identity. Whenever you talk about an original, if you talk about A inverse, if you name the original matrix A and you talk about its inverse, you use this notation. A, it's not read A to the -1, even though that's what it looks like. You read it A inverse. And so anytime you multiply on your notes, this looks like a big dot, A times A inverse, or A inverse times A, you will always get the identity. So we're going to learn how to find the inverse of a 2 by 2 matrix. Any matrix M whose entries are A, B, C, D will have an inverse, will have M, it looks like M to the -1. You can find M inverse, and this says IFF, and do y'all remember what this notation means with the straight bars on either side? That's the determinant. That's the notation for the determinant. So if the determinant is not 0, write yourself this note. If a matrix has a determinant of 0, then it does not have an inverse. If a matrix has a determinant of 0, then it does not have an inverse. go scroll this up, because we need to learn how to find a 2 by 2, the inverse for a 2 by 2 matrix. It's hard to scroll if I need to scroll again. This is good right now. Just if I need to scroll it, I'll get you to do. Okay. So look at this. Any matrix M whose entries are A, B, C, D will have an inverse called M inverse if and only if the determinant is not equal to 0. So we talked about that. Here's the process for finding M inverse. You're always going to do 1 over, tell me what this is, AD minus BC. AD minus BC. That is the determinant, right? So, and then, another way to say this is 1 over the determinant of M times, not the original ABCD, but we're going to do a modified version of the original matrix. So we're going to do 1 over the determinant. Now look how we modified it. See if you can explain to me what we're doing here. Here was the original, A, B, C, D. Here's the modified one. Could you explain what we did to modify it?
You made the C and B's negative,
Okay.
and you flipped A and D.
You got it, exactly. Along the principal diagonal, we trade places, switch those. And along the other diagonal, we change signs. Okay, that's how you modify it. So, example. If Q is equal to this, find Q inverse, and furthermore, verify that you found it. So first, we're going to find, the very first thing that we got to do is find the determinant of Q. Remember how to do it? Start in the upper left, multiply. That means do 2 times negative 3 minus 1 times negative 1. That'll give you negative 6 plus 1 or negative 5. So then to find Q inverse, we're going to do 1 over negative 5 times a modified version of the original Q matrix. Remember what we said we're going to do? Along the first diagonal, we're going to trade places. So, negative 3, positive 2. And then along the second diagonal, it's going to look like we trade places again, but we're not trading places. We're changing signs. Positive 1 turns into negative 1. Negative 1 turns into positive 1. So I have a scalar to multiply by every entry inside the matrix. Here is Q inverse. Negative 1/5 times negative 3, a negative times a negative turns into a positive 3/5. Negative 1/5 times 1, that's negative 1/5. Negative 1/5 times negative 1, that's positive 1/5. And negative 1/5 times 2, that's 2 over 1. Remember, we're going straight across the top, straight across the bottom, so we get negative 2/5. Are you okay? Now, for the purposes of this video, so that it'll show up on the screen, I'm going to keep going over here. You probably don't want to do that because you've got another problem too to work here in a minute. But when it says verify the result, prove that what you found really is the inverse, here's how you do it. You're going to have to multiply the original matrix Q times the inverse, or what we think is the inverse, to see what happens. So if you multiply the original Q, 2, negative 1, 1, negative 3, times what we think is the inverse, 3/5, negative 1/5, 1/5, negative 2/5. If we multiply those, we have a 2 by 2. times another 2 by 2. Is it possible to do the multiplication? Yes, it is. In fact, we'll get a 2 by 2. So to get this entry right here, remember we've used row 1 in the first, column 1 in the second, so we'll do 2 times 3/5 plus, move across, move down, -1 times 1/5, straight across the top, straight across the bottom. What do we have? 6/5 minus 1/5. What's that? 6/5 minus 1/5. That's 5/5 or 1. This entry right here, we got to go across row 1, down column 2, so that'll be 2 times -1/5 plus -1 times -2/5. So that'll turn into -2/5 and +2/5, and that gives us 0. What is supposed to happen when I multiply two things that are inverses? We just talked about it a little ways up the notes. We should get the identity. Looking good so far, right? What should we get right here if it's working like it's supposed to? We should. So that's row 2, column 1. So we'll do 1 times 3/5 plus -3, 1 times 3/5 plus -3 times 1/5. So that is 3/5 minus 3/5. We get 0. So for the last entry right here, if it's working like it should, if this is really going to be the identity, I should get a 1. It's row 2, column 2, -1/5, +6/5. If you do -1/5 plus 6/5, that gives you 5/5 or 1. So when you do Q times Q inverse, we get the identity. You have to verify it both directions because usually when you multiply matrices, order makes a difference. You don't get the same thing when you multiply when you change the order of multiplication. But if they are inverses, you will. So then you got to go ahead and verify and multiply Q inverse times Q. So we got to multiply 3/5, -1/5, +1/5, -2/5, times our original Q, 2 -1, 1 -3. Here we go. I'm going to erase this so it doesn't confuse everything. Hopefully you can follow yours on your notes. But if we multiply, then this entry right here, row 1, column 1, this will give straight across the top 6/5 minus 1/5. That's 5/5. We get 1. This entry right here, row 1, column 2, -3/5 and +3/5. If you have -3/5 plus 3/5, you get 0. This entry right here, row 2, column 1, we've got 2/5 minus 2/5. Yep, that's 0. And this entry right here, straight across, straight down, -1/5, +6/5. That's 5/5, -1/5, +6/5. That's 5/5 or 1. So if you, in order to verify, and it's kind of tedious, but to verify that you really did find the right inverse, you multiply both directions and see if you get the identity both ways. So work on this one for just a minute while I erase. Find P inverse. What's the first thing you have to do to find P inverse? Find the determinant. Good deal. So the determinant means start in the upper left. The determinant is 14 minus 0, 14. So after you find the determinant, here's how you get the inverse. We're going to call it, it looks like P to the -1. It's red, P inverse. It's going to equal, let me back up. Does P even have an inverse? Is it possible to find one? Yes, how do I know? Remember what we said up here? As long as the determinant is not 0. If you ever do this and you get a determinant of 0, you can't find an inverse. Why? 1 over 0 is undefined. Something undefined times something else, who knows? So if the determinant ever is 0, then you can't find an inverse. But in this case we can. So we do 1 over 14 times modified version of the original. Remember, on the first diagonal, trade places, 7, 2. On the second diagonal, change signs. Well, 0 doesn't have an opposite sign, so it's still 0. But positive 5 turns into negative 5. Negative 5 turns into positive 5. So you've got a scalar to multiply by every entry inside the matrix. And when you multiply the scalar, reduce. So straight across the top, that's 7 over 1, 1 over 14. We get 7/14, but reduce that. Call it 1/2. 1/14 times 5, we'll leave that 5/14. 1/14 times 0 is still 0. And 1/14 times 2 will give us 2 over 14, but let's reduce it and call it 1/7. Now, for the sake of time, I'm not going to verify this, but I might ask you to on your homework or on your quiz. Do you know how to verify it, just like we did this other one over here? You would have to multiply P times P inverse and show that you get the identity. And in the other direction, P inverse times P and show that you get the identity. If you're asked to verify, that's what you need to do. Will you scroll up, Michael?
Yeah.
So on the back side, we're going to use inverse matrices to solve a system of equations. And if we're going to do that, the very first thing that we have to do is change the equation, change this system of equations that we have right now to a matrix equation. So you're always going to have a coefficient matrix, 6, 5, 5, 4, and a variable matrix, x, y, and a solution matrix, 13, 10. Now, if I had not shown you how the multiplication process works, this wouldn't make very much sense to you. But because you know how to multiply, you have a 2 by 2, and this is a 2-story building with only 1 column, so a 2 by 1. Is it possible to multiply these two? Yes, because the inside dimensions match. And furthermore, the answer would be a 2 by 1. Because you know how multiplication works, then you could go, well, if I were trying to get this entry in my answer, I would go across row 1 and down the column. So it would be 6 times x plus 5 times y equals 13. That equation, exactly. And you would go across row 2 and down the column, 5 times x plus 4 times y equals 10. So because we learned how to multiply by hand, then this matrix equation, hopefully you can look at that and say, oh, I realize that means exactly the same as this system of equations the way we usually see it. Okay, so now, once you have a matrix equation, how do you solve it? We're going to call this one matrix A. And the one that we're trying to look for, I'm really trying to figure out what are the values of x and what are the values of y. So this one's going to be matrix X, and my solution matrix is matrix B. Nick, if you want to come get a copy of this. Okay, yeah, that's fine. And here's a copy of the notes if you're going to look at those with us. We're on the back side. So let's talk about this for a minute. Remember, this is not just any old algebra equation. This is a matrix equation. So A times x equals B. If this were just a plain algebra equation, you'd tell me to solve for x, divide by A on both sides. However, remember this, we don't divide with matrices. So we have to go with another plan. Our other plan is to remember, if I multiply A inverse times A times x, can you move that cursor? Then whatever I do on one side, I have to do the same thing on the other side. A inverse times B. And we're always going to put it on the left, because A inverse is going to be a 2 by 2. And if I put it on the other side, if I if I had this one is a 2 by 1, and if I wanted to multiply it with a 2 by 2 on the right side, would I be able to do that? The dimensions wouldn't match. So we're going to always put A inverse on the left, because it's going to be a 2 by 2. If I were going to be able to do the multiplication, I'd have to have a 2 by 2 on the left, and then I could multiply it. So it matters where you put it. Why did that help us? Why does all of a sudden multiplying A inverse times A help us any? What's A inverse times A?
It's gonna equal 1.
Well, in matrix lingo, the identity, right? So the identity times X equals A inverse times B. But you remember what the identity is? 1, 0, 0, 1. When you multiply that matrix times any other matrix, what answer do you get? The original matrix. So you're right, Greg. It's like multiplying by 1. We just get X. So the process that we're going to go through is we're going to multiply A inverse times B in order to solve for X. Really, that's what all of this is telling you. All of this is the same thing as I just wrote right there. So in order to solve for X in the variable matrix, we're going to have to multiply the inverse of A, the inverse of the coefficient matrix, by the, and there's a typo right here, this should say, by the solution matrix. So down here, where it says solve for X, in order to do it, in order to find the X matrix, which is made up of our two variables, X and Y, we're going to have to multiply A inverse times our B matrix, 13, 10. In order to be able to do this, what is next? What are we going to have to do? If I know that I need to multiply A inverse times B, I got to find A inverse. So here we go again. To be able to find A inverse, you remember the process? It's a process that you just have to memorize. 1 over the determinant times a modified version of the original matrix. So if A is this, A is 6, 5, 5, 4, then A inverse is, you got to help me find it. Determinant first. Determinant is 24 minus 25 or negative 1. So A inverse is going to be 1 over the determinant, 1 over negative 1, times a modified version of the original matrix. So remind me, what do I have to do to modify this? Y'all still there?
I'm sorry. You need to flip 6 and 4.
Okay.
And then make both 5s and 5s.
There you go. Along the first diagonal, trade places, so not 6, 4, instead 4, 6. And along the other diagonal, change signs, so these both become negative 5. 1 over negative 1 is really just negative 1, right? So distribute negative 1 to every entry in the modified matrix. So negative 1 times 4, negative 4. Negative 1 times negative 5, positive 5. Negative 1 times negative 5, positive 5. Negative 1 times 6, negative 6. So there's our inverse. So after we have found A inverse, it goes here. So if you put negative 4, 5, 5, negative 6, you're multiplying A inverse times B. Can you do this multiplication? You got a 2 by 2 times a 2 by 1, and you can multiply that. The answer is going to be a 2 by 1. And furthermore, the answer that you get is really going to represent your x, y values. So if you set up a 2 by 1 matrix, here we go, to find this entry right here. It's row 1, column 1. That means in the first matrix I go across row 1, I'll do 4 times 13, or negative 4 times 13, plus, move across, move down, 5 times 10. So that's negative 52 plus 50, negative 2. Do this one. You gotta use row 2, column 1. So 5 times 13 plus, what did I do? Oh, 5 times 13 plus negative 6 times 10. So that's 65 plus negative 60. We get negative 5. No, positive 5. Sorry. 65, negative 60. 65 minus 60, we get 5. So you just solved this system of equations. The solution is negative 2, 5. Check it. 6 times negative 2, negative 12. 5 times 5, 25. Negative 12 plus 25, yep, you get 13. 5 times negative 2, negative 10. 4 times 5, 20. Negative 10 plus 20 gives you 10. Okay, and you're thinking, I think I could probably solve that system of equations way faster than doing all of this, and you could. But remember that the advantage of using an inverse matrix is when you have a big system. This really helps. So let's look at one more. Can you scroll up, Michael? So this time, we're going to solve a system of 3 equations. And the first thing you have to do is convert this normal-looking system of equations to a matrix equation. So notice there's not a y. You're going to have to think of this as x plus 0y plus 2z equals 6. Negative 1x plus 2y plus 3z, that one has everything. This one is missing a z, so you're going to think of this as x minus y plus 0z equals 6. When you change it to a matrix equation, you will always have a coefficient matrix, so you'll use 1, 0, 2, negative 1, 2, 3, and 1, negative 1, 0. And you'll have a variable matrix, this time, x, y, z, and a solution matrix, 6, negative 5, 6. And because you learned how to do matrix multiplication by hand, you understand that to get this entry right here, you would go across the top row, 1 times x plus 0 times y plus 2 times z equals 6. So do you believe that this matrix equation really is the same thing as this equation, this system of equations? Okay, good. Now, here's the good news. I'm not going to make you learn how to find the inverse of a 3 by 3 or a 4 by 4 or a 5 by 5 without a calculator. But for this homework, I'm not going to show you how to do it on the calculator today either. For this homework, if you need the inverse for a 3 by 3 or a 4 by 4, it's going to be given to you. So use the fact that the inverse of, here's matrix A, is given to you. Here's A inverse. So A inverse is already given. Remember the process that we're going to use to solve a matrix equation. This one is matrix A. The thing we're looking for is our variable matrix. We're going to call it X. And our solution matrix equals B. If I ask you, so I'm going to go through this again, just so it sticks with you. If I ask you to solve a matrix equation, A times X equals B. Usually, for an equation like this, if I said solve for X, you'd tell me divide both sides by A. But since A represents a matrix, we don't divide by a matrix. So we have to go to plan B. Plan B is to know that if I multiply A inverse, and we need it on the left, A inverse times A times X, and if I do the same thing to both sides, then I'll do A inverse on the left times B. That helps me. I really don't even have to do this multiplication because I know if I did it, I would just get the identity. 1, 0, 0, 0, 1, 0, 0, 0, 1. I'd get the identity times X. And when you multiply the identity times x, it's like multiplying 1 times something. So x, the matrix that we're looking for, we're going to get by doing A inverse times B. So over here, to solve for x, we're going to do A inverse times B. So let's fill it in. Our x matrix is our variables, x, y, z. A inverse is already given to us. We didn't have to find that one, so this goes here. 3, -2, -4, 3, -2, -5, -1, +1, 2. And we're going to multiply that times our B matrix, which is our solution matrix, 6, -5, 6. Is it possible to do this multiplication? Well, we got a 3 by 3, and then we got a 3-story building with only one column, a 3 by 1. Yes, we can multiply, and in fact, when we do, the answer is going to be a 3 by 1. And the 3 by 1 answer that we get is going to equal x and y and z. So, here's the solution. X, y, z equals what we get when we do this multiplication. So this entry right here, that comes from row 1, column 1. That means I'll do 3 times 6 plus, move across, move down, -2 times -5 plus, move across, move down, -4 times 6. So where do we land? 18 plus 10 minus 24, or 28 minus 24, 4 for this entry. Let me give you a minute. You do this one. You should get -2. I know I'm kind of rushing you a little bit. Did y'all agree? Did you have time to get it? Anybody have the last one? Oh, I wasn't rushing y'all at all. So tell me what this means. What does this answer mean? What's the answer to my solution, to my system of equations here? And if we write it as an ordered triple, 4, -2, 1. Here's your assignment. Can you do it? Steely, will you punch that button? You did an awesome